Hello. In this video tutorial, we're going to be taking a look at AP Physics 1, Unit 3 Workbook. We're going to start with Activity A. Please remember to pause or rewind the video as needed. Read along this scenario with me. Angela is in a stopped car at a traffic light when the light turns green and she accelerates. Part A. Sketch and label the vectors for velocity, acceleration, and net force on the car. Again, this is not a free body diagram. Well, if the car is starting from rest, that means the velocity is 0 at the moment the light turns green and she accelerates, so the velocity starts from 0. The net force and the acceleration are both in the forward direction. Which way does Angela's body feel pushed? Explain in a short sentence why she feels this way. Well, she feels pushed backward because she was at rest and her body wanted to remain at rest. So she feels the back of her seat pushing her forward while her head remains at rest. It feels like something is, quote, pushing, unquote, her head back. When in reality, this is Newton's first law. Objects at rest stay at rest. So her body is at rest with the car who's at rest. The car accelerates, pushes on her back, so her back and her body accelerate along with the car. However, her head tries to remain at rest. And so that's where you feel the push backwards, which really isn't a push at all. It's just your head being left behind. Part B, as she approaches a stop sign, she slams on the brakes. Sketch and label the velocity vectors for acceleration and net force of the car. Well, the velocity is still going forward even though you're slamming on the brakes, but when you're slowing down, the acceleration opposes velocity and is now going backward, and net force always goes the same way you accelerate, so net force is also going backward. Which way does Angela's body feel pushed? Well, forward. Which way is the car accelerating? Backward, as is the net force on the car. Part C. As Angela continued driving, she rounds a corner at constant speed. Sketch and label the vectors for velocity, acceleration, and net force. Well, velocity is tangent to the curve, and that is because you want to keep going the way you're going, and it's only a net force that can change your velocity, change your direction, speed you up, slow you down, whatever. Well, in this case, it's the centripetal acceleration that is causing the curvature around the edge. And so while the velocity goes tangent to the circle, meaning straight ahead, the acceleration and the net force are both pointing to the middle. They are centripetal acceleration and force. Centripetal refers to center pointing. We're talking about pointing toward the center of a circular curve. Which way does Angela's body feel pushed? Well, she feels as though she's pushed to the outside of the car. The car, however, is accelerating towards the center as the net force is pointing towards the center. Why does Angela feel this way? Why does Angela feel as though she is basically moving towards the outer edge of the car? Well, you got to remember, Angela's body, as the car was right here approaching the curve, Angela is driving the car, and the car is going forward, her body's going forward along with the car. As the car starts to turn left, her body still kind of wants to go forward a little bit. So she's going to feel as though she's leaning to the right because her inertia is taking her forward. Her inertia, meaning her resistance to changing velocity, is taking her forward direction. And it's only the seatbelt that's really accelerating her along with the car. That's why her body would lean towards the right. AP Physics Workbook, Unit 3, Activity B, Direction of Acceleration and Velocity. Read the scenario along with me. A car is traveling along a road. Air resistance can be ignored. Part A, for the following situations, determine if the car is speeding up, slowing down, or staying at a constant speed and turning clockwise, counterclockwise, or not turning. We have 4 scenarios we're going to look at. Okay, and I'll label them A, B, C, D. A, B, C, and D, just to give them reference. In A, you are moving forward, right? But you only experience acceleration to the left, meaning you are moving at a constant speed. And because you're moving at a constant speed, you are moving with, this acceleration would be only centripetal acceleration. It would only be A sub C. And since it's causing curvature to the left, you would be turning, as you can see in the picture, in the counterclockwise direction. Part B. Part B, you have a situation where your acceleration is not directly pointing to the left. See, this would be centripetal acceleration pointing to the left. Because it's pointing a little bit forward, you also have a little bit of what's called tangential acceleration. That means acceleration in the direction of velocity, in the direction of your changing velocity. And this tangential and centripetal acceleration lead to an overall acceleration pointing at that angle. Now, in order to achieve this, you have to have acceleration in the direction of motion. And what happens when we accelerate in the direction of motion? We speed up. Okay, and we'd still be curving to the left, so you'd still be moving clockwise. Letter D now has the velocity coming of the reverse of the car, so we're backing up. Apparently we're backing up, but there's acceleration pointing to the left of the car again, which means we're curving this way. And since velocity is perpendicular to the acceleration, we're going to be moving at a constant speed. In the clockwise direction. Now for letter D, you don't just have your centripetal acceleration, you also have tangential acceleration, but this time the tangential acceleration is opposing velocity. And the overall acceleration is, of course, pointing in this direction here. So if you have tangential acceleration opposing velocity, that means you must be slowing down. And since you are moving forward as you're doing this, you are going to still be curving counterclockwise. Okay, let's quickly summarize. If the acceleration is 90 degrees from the velocity, you move at a constant speed. And we see that in letter A and C. If the angle between the acceleration and the velocity is an acute angle, meaning less than 90 degrees, you're speeding up because you have some tangential acceleration in the direction of motion, allowing for that speeding up to happen. And lastly, if your angle between the acceleration and velocity is obtuse, meaning greater than 90 degrees, then you are slowing down because you now have tangential acceleration that's opposing velocity and thus slowing down. AP Physics Workbook, Unit 3, Circular Motion and Gravitation. Activity C, Centrifugal Force. Read the scenario along with me. A dump truck is making a very fast left turn as shown. In the back are 2 blocks of ice, one big mass M and one mass M little m, where big M is greater than little m. The truck does not roll over. Part A. Sketch the path of the left and right mirrors take during the turn. We can see from the picture, the left mirror would take this path right here, and the right mirror would take this path right here. Part B. Using two different colors, sketch the paths of the blocks the ice takes during the turn. Assume that the friction between the bed and the truck and the ice may be neglected. Well, the little block of ice wants to go straight. And the big block of ice also wants to go straight. Part C. Your friend, who is not in physics class, says the blocks go to the outside of the truck because of a centrifugal force is acting on them. In a few brief sentences, explain why your friend is incorrect. Reference the diagram above in your answer. The reasons both blocks appear to go to the outside is that they were moving in a straight line. And according to Newton's first law, all objects in motion want to stay in motion unless a net force accelerates that, meaning speeds up the object, slows it down, or in this case, changes direction. So the blocks of ice are basically going in a straight line. And since there is no net force to change their direction along with the truck, they keep going in a straight line. It appears as though they go to the right or move to the outside of the truck, when in reality, they're just simply going straight and the truck is moving to the left out from under them. Part D. The truck then approaches another intersection to make a turn. The truck can either make a left turn or a right turn as shown in the diagram. Assume the truck approaches, makes the turn, and continues in the new direction without changing speed. The centripetal force for the turn is provided by the force of static friction, which is determined by the relationship friction equals mu times normal force. In a few short sentences, explain why static friction and not kinetic friction is exerted on the truck even though the truck is in motion. As the truck makes the turn, it does not skid. Therefore, static friction is preventing the skidding as the turn is being made. Think of it this way. Static friction makes a point of contact with the ground to prevent sliding or skidding. In fact, static friction causes the rolling of the tire. We will learn that later on as a torque, a rotational torque. But the static friction provides the force to make the turn. If the car were skidding or sliding in any way, then it would be kinetic friction. But the fact that the car does not skid or slide as it makes the turn means that static friction is the reason why it is able to make the turn. Part E. In a few short sentences, explain what happens to mv squared is greater than the value of mu times normal force. Well, if mv squared over r is greater than mu times normal force, then there will not be enough static friction to provide the centripetal force to make the turn. The truck will then slide off the road. Which turn would the truck allow to slow down more in order to make the turn safer? Well, if you look back at the picture, the left turn is a much wider radius. The right turn is a much smaller radius. If the centripetal force is equal to mv squared over r. Okay, so let's take a look at that. We have, and the centripetal force is friction in this case, static friction. If the radius is higher, then the speed can also be higher in order to have the same amount of friction holding the car to the road. So again, if the radius is larger, V can be larger with the same friction force. If the radius, on the other hand, is smaller, then V needs to be smaller too in order to have the same friction. You would have to slow down more on a smaller radius turn. Therefore, you would have to slow down more for a right turn than a left turn. Unit 3 Workbook. Activity D, Vertical Circles. Read the scenario along with me. A ball whose weight is 2 newtons is attached to the end of a cord of length 2 meters as shown. The ball is whirled around in a vertical circle clockwise. So like this. The tension at the top of the cord is 7 newtons and the tension at the bottom is 15. Two students discuss the net force of the ball at the top of the circle. Dominique says, the net force of the ball at the top position is 7 newtons. This is sensed because the net force is the same as tension. Carlos says, no, the net force on the ball includes the centripetal force, tension, and weight. The tension and weight are acting downwards and have to be added. Then you need to figure out what the centripetal force, mv squared over r, and include it in the net force. Part A, cross out the incorrect statements for each student's argument. This is one of those examples where neither student is completely right. In fact, this happens. Everything Dominique says is wrong. Let's draw a free body diagram at the top and the bottom so we can clarify. The forces acting on the ball are tension and weight. Both act towards the center of the circle when the ball is at the highest point. Therefore, you would add those forces and those total would become the net force. At the bottom of the swing, tension acts inward to the center of the circle and weight acts downward but out of the circle. Carlos is wrong in that centripetal force is not something to be added. Tension and weight are a part of this, and they both act downward, and they both have to be added. But you do not add a centripetal force. These are providing the centripetal force. So just to clarify, centripetal force is not an additional force. It is simply a description of any force that causes circular curvature. Part B. In a few short sentences, state the net force on the ball at the top of the circle and support your claim with evidence. Carlos is correct in that the net force includes the weight and the tension force, and they both point down, so they will be added together. Therefore, the net force on the ball at the top of the circle is actually 7 newtons plus the 2 newton weight, which equals 9 newtons. These two forces add together to be the centripetal force. Part C, the diagram to the right, shows the circular path of the ball from Part A. The dots below represent the ball at marked locations on the circular path. Draw on the free body diagram showing and labeling the forces, not components, exerted on the ball at each point. Draw the relative lengths of all vectors to reflect the relative magnitudes of all forces. Unit 3, AP Physics 1 Workbook, Activity E, Maximum Speed Over the Top. A scenario is as follows. A car of mass m passes over a bump in a roadway that follows the arc of a circle of radius r as shown. Part A, using representations. The dot at the right below the picture represents the car at the top of the hill. Draw a free body diagram showing and labeling the forces, not components, exerted on the car. Draw the relative lengths of all vectors to reflect all relative magnitudes of the forces. Each force must be represented by a distinct arrow starting on and pointing away from the dot. Well, at the very top, let's see here. we would have the weight going down at the very top, and you'd have the normal force, right, going up. Okay, but remember, the one pointing in towards the center of the circle has to be greater in magnitude. So weight, or Fg, equals mg goes down, and we're going to draw the normal force as shorter. Forces in must always be greater than forces out. Part B, starting with Newton's second law, derive an expression for the minimum speed v the car can have without losing contact with the road. For each line in the derivation, explain what was done mathematically. In other words, annotate your derivations. Your expression should be in terms of r and physical constants. The first one says net force equals ma. Description: the net force on the car at the top of the hill is equal to the acceleration of the car times the mass of the car. Next step, weight minus normal force equals mv squared over r. We have taken the net force and split it into forces going into the circle minus forces going out of the circle. Description: there are two forces exerted on the car at the top of the hill, the weight downward and the normal force upward. The weight is directed toward the center of the circle, and the normal force is directed away from the center. Next step. If the car is going the maximum speed, the car loses contact slightly with the ground, and thus the normal force goes to zero. So we are left with weight equals mv squared over r. As weight, the gravitational force, is the only contributor to the centripetal force curvature. We're going to rewrite the weight is mg, and the masses cancel. Last step, we're going to solve for v rather. Multiply both sides by r, and then square root. Part C. In your derivation, you set the normal force equal to 0. Why? The maximum speed of the car will be when the centripetal force is equal to the weight. At that point, only the weight contributing to the curvature. If the car goes too fast, it will completely lose contact with the ground. So as it approaches maximum speed, the normal force has to approach 0. Part D. A truck of mass 2m passes over the same bump. Compared to the car, how many times bigger or smaller is the maximum speed without losing contact with the ground? Justify your answer with reference to the expression in Part B. The maximum speed of the truck is the same, and it is the same regardless of the mass, whether it's a truck, a car, or a bicycle. The mass cancels out of the equation. Okay, if we draw forces acting on the ball at these locations right here, as it is moving clockwise, at point M, you have inward tension and weight is pointing straight down. Now the weight should be the exact same length no matter what. So I'm just going to copy that all the way around the circle, just like that. Now, in addition to the weight is the tension. So at the bottom of this, tension is going up to the center of the circle. At point P, tension is going to the right towards the center of the circle. And at the top, point Z, tension is pointing down, and therefore it needs to be added. Here, tension and weight need to be subtracted because they're pointing in opposite directions. Here and here, only tension provides a centripetal force because weight is perpendicular. So drawing the relative lengths, let's make sure that the weight is the same length. And since weight is always directed downward, I'm going to put the weight on each one. Okay, at point Q, you've got tension pointing up and weight pointing down. And since tension is pointing to the center of the circle and it causes the curvature, the force pointing to the center of the circle needs to be larger. Force in is greater than force out. Okay, at point P, you've got tension pointing to the right towards the center of the circle. Z, you've got tension and weight, both applied down. And at point M, you have tension going left, right, and weight going down. Part D. Derive an expression for the minimum speed that the ball can have at point Z without leaving the circular path. For each line in the derivation, explain what was done mathematically. The first line is completed for you as an example. Net force equals MAC. Description: the sum of forces is equal to MA, and since the ball is in circular motion, A is the centripetal acceleration. Okay, next up. Centripetal force can be represented by velocity squared over the radius. So what I'm going to do is I'm going to substitute for AC. And net centripetal force is equal to mv squared over r. So we're substituting AC for v squared over r. Next step, the two forces at the top of the circle are tension and weight. So now what we're going to do is we're going to represent the net force as the two forces, tension plus weight, equal mv squared over r. At minimum speed, the tension goes to 0. So that means we're only left with mg equals mv squared over r. And only the weight causes curvature. So only the weight is now the net force. The masses cancel and the equation is rearranged to solve for velocity. And so we get v is equal to the square root of g times r. Suppose the string breaks at point P. Describe the motion of the ball after the string breaks. When describing the motion of the object, you need to discuss what is happening to the position, velocity, and acceleration of the object. Tell the story of motion from the ball, from the time the string breaks until it reaches the ground. The ball travels up, straight up to a maximum height, and then comes straight back down. The speed of the ball decreases until reaching maximum height, at which the ball turns around and speeds up until it hits the ground. The acceleration of the ball is constant 9.8 meters per second down after the string is cut.